Hello, everyone. A warm welcome to all of you, and thank you for joining the session today. My name is Madhu from Synchronous Technologies, USA. Today, I will be speaking on a topic that is becoming more crucial in the modern IoT ecosystems. Edge AI for smart camera IoT devices, real time image processing without cloud dependencies. Now, before we dive in, let's frame the big picture. For years, IoT cameras have been heavily dependent on cloud. But the current real world requires something faster, more private, and more efficient. And that's what exactly Edge AI steps in. Cloud Central bottleneck. Before we understand why Edge AI is so important, we first need to understand the limitations of the traditional cloud based approach. This slide explains the major bottlenecks that occur when smart cameras depend fully on cloud processing. Bandwidth becomes a major problem. Every camera that streams video to the cloud consumes network bandwidth. As soon as you add more cameras, the bandwidth requirement rises rapidly. In real world places like construction sites, rural areas, and densely urban neighborhoods, network strength is unusually limited. So, when multiple cameras try to stream raw video at the same time, the systems become slow and unstable. We can simply say the network cannot handle so much continuous video traffic. Latency is too high for real time use. When everything goes to the cloud, the device must wait for the video to upload, for the cloud to process it, and then send the results back. Even in good conditions, the delay can be 50 to 500 milliseconds. For real time applications like security alerts, industry automation, or safety monitoring, this delay is unacceptable. The system must react immediately, not half a second later. Privacy and compliance issues. Sending a video to the cloud raises privacy concerns. Users do not want their personal live footage uploaded continuously. Regulations like GDPR and CCPA make this even more challenging. Edge AI solves this by keeping data local and sending only essential information. High cloud costs. Streaming video non-stop requires cloud compute, storage, and bandwidth, all of which cost money. At scale, with dozens or hundreds of cameras, the cost become unsustainable. So the traditional cloud-only setup does not scale. It is too slow, too expensive, and too dependent on strong internet. This is why industry is shifting towards Edge AI. Now we understand that the cloud problems. Let's look how Edge AI can solve these problems. This slide explains why running AI directly on device is such a powerful shift. Processing happens directly on device. With Edge AI, the camera does not send video to the cloud for analysis. Instead, the AI model runs next to the camera sensor. This makes detection and decision making almost instant because there is no network delay. Huge reduction in bandwidth. Instead of streaming full video, the device only sends important events such as person detected or object found. This reduces the bandwidth usage by 85%, making the system much more easier to deploy anywhere, including low connectivity environments. Big improvements in battery life. Because the device uploads for less data and performs fewer network operations, battery life will be more. In many cases, battery life improves by 4 to 5 times, which is critical for outdoor cameras and IoT devices. Under 50 milliseconds latency enables real-time performance. The AI runs locally, there is no wait time for cloud response. This system can process frames in under 50 seconds, enabling real-time alerts, tracking, and analysis. Better privacy and security. Since the raw video stays on the device, user maintains full privacy. Only the final result, not the video, is shared to the cloud. This is a major advantage in smart home systems, public environments, and regulated industries. So Edge AI completely changes the game. It gives us speed, efficiency, privacy, and reliability, all directly on the device. This is why modern IoT camera systems moving away from the cloud dependence and adopting edge first approach. Evolution of IoT cameras. To understand why Edge AI is so important today, let's quickly look how IoT camera systems have evolved over the years. This slide shows three major stages in their development. Early local processing. In the beginning, cameras had very limited hardware. They could only do simple tasks like detection motion, recording a video, or sensing alerts. There was no intelligence, just basic device behavior. These early systems were reliable but extremely limited. Cloud dependence intelligence. As cloud computing became more popular, companies started shifting all the heavy processing to the cloud servers. This allowed cameras to perform more advanced tasks such as facial recognition, object detection, behavioral analysis. But this comes up with several problems. Bandwidth usage cost is high, increased latency, privacy. This was the phase where people realized that relying completely on cloud was not scalable. The edge intelligence era. Now we are in the third phase. Modern embedded hardware has become more powerful enough to run AI models directly on the device. Today, smart cameras can do real-time detection, classification, anomaly detection, low light, all on the device itself. This evolution has brought us to the point where Edge AI is not optional. It's becoming the standard approach for all IoT camera systems. Network optimization techniques. This slide outlines the main techniques we use to make AI models small, fast, and efficient enough to run on edge devices. Let's go through each one in the simple terms. Quantization reduces the precision of the numbers inside the model from 32-bit to 8-bit and helps reduce the power usage with very little impact on accuracy. Knowledge distillation. This is a training technique where big model teaches the small model. The small model learns how to perform almost as well as the big one, but with a fraction of size and compute requirements. Architecture selection. Here we choose model structures that work well on limited hardware. Models like MobileNet, SqueezeNet are designed specifically to run on mobile devices and IoT devices. Neural architecture search can also automatically generate efficient designs. Pruning removes unnecessary parts of neural network. It gets rid of connections that don't contribute much to the performance by reducing the model size and speeding up. Efficient architectures. Finally, we adapt to lightweight model families such as MobileNet and SqueezeNet. These models use depth-wise convolutions and streamlined layers to maintain good accuracy while staying extremely small. All these techniques work together to transform heavy cloud-based model into an edge-friendly one. Edge AI acceleration. Now let's talk about hardware that makes Edge AI possible. This slide explains why specialized processors like TPUs and NPUs are critical for AI on small devices. Why CPUs alone are not enough. Traditional CPUs are general purpose chips. They can do a bit of everything, but they are not optimized for heavy matrix calculations that AI models require. Running AI solely on CPU would be slow and consume a lot of power. The role of TPUs and NPUs. This is where TPUs, tensor processing units, and NPUs, neural processing units come in. These chips are designed specifically for AI workloads. They contain parallel processing units, fast matrix multiplication engines, optimized memory pathways. This makes them 10 to 100 times more efficient than CPUs for AI tasks. Example of edge acceleration. Some examples include Google Coral TPU, Qualcomm Hexagon DSP, Apple Neural Engine. These accelerates allow IoT cameras to run complex models while staying energy efficient. Without these hardware accelerators, real-time AI on battery-powered cameras simply would be not possible. This slide presents the full system architecture used to run AI efficiently on edge devices. It's organized into three main layers that work together. HAL. HAL hides the differences between various hardware platforms. It provides a consistent interface for memory, sensors, and compute functions. This allows us to run same AI code on different devices without rewriting everything. Neural network optimization layer. This is where model gets transformed into an edge-ready version. It goes through quantization, pruning, architecture selection, and compilation. The output is small, fast, and efficient model, tile efficient to the device's capabilities. Real-time processing pipeline. This pipeline is responsible for handling the live video stream. It manages frame capture, pre-processing, AI interference, and post-processing. This goal is to maintain smooth real-time performances no matter how busy the device gets. The layered architecture ensures flexibility, efficiency, and reliability across wide range of hardware platform. Hardware platform support. This slide shows the different hardware platforms we support, from very simple devices to advanced edge processors. Entry level devices. These are basic systems with 512 MB to 1 GB RAM, such as ARM Cortex processors, Adreno boards with external accelerators. They can handle lightweight models for basic detection tasks. Mid-range platforms. These include devices like Raspberry Pi 3 and Raspberry Pi 4. They are popular for smart home and consumer camera applications. They offer good balance between cost, performance, and power usage. High-end edge processors. These platforms are designed specifically for industrial or professional applications. Examples include Google Coral TPU, Qualcomm Hexagon DS, NVIDIA Jetson modules. These systems support large models, faster interface, and more complex analytics. Supporting this wide range of hardware ensures that our edge AI solutions can use anywhere, from low-cost home devices to advanced industrial systems. Neural network optimization pipeline. This pipeline is essential because it prepares our AI models to run efficiently on small, resource-limited edge devices. Remember, cloud models are often large, slow, and power-hungry. Edge devices cannot run such models directly. So we use a three-stage optimization pipeline to convert a standard neural network into an edge-optimized version. Architecture selection. That is the stage one. Choosing highly effective architectures like MobileNet, SqueezeNet. MobileNet v3 optimized for general vision tasks on mobile or edge hardwares. SqueezeNet extremely small footprint, ideal for very constrained environments. Lightweight encoder-decoder networks with residual connections achieve 2 to 5 MB model sizes. These models use techniques like depth-wise separable convolutions and efficient residual blocks, allowing them to run quickly while keeping accuracy high. Quantization stage 2, where the model becomes truly edge-friendly. A standard AI model uses 32-bit floating point weights, FP32. But FP32 is very heavy. It takes more memory, more energy, and more compute. So we apply quantization, converting FP32 values to 8-bit integers. This gives 4 times reduction in model size, faster interference speed, much lower power consumption. The accuracy loss is usually under 2%, which is completely acceptable for most applications. Stage 3, platform-specific compilation. This is where we use edge-focused compilers such as TensorFlow Lite for ARM processors, Edge TPU compiler for Google Coral, Hexagon NN compiler for Qualcomm NPUs, specialized compilers for NPU TPU acceleration. During compilation, the system performs graph optimization, which removes unnecessary operations. Operator fusion combines multiple operations into one for speed. Memory layout optimization. This makes sure memory access is efficient. This stage ensures that every part of model runs on most efficient compute unit available. CPU, NPU, RT, real-time processing architecture. Now let's see how real-time processing pipeline works inside on Edge AI camera. This pipeline is designed so the camera can continuously process videos at 30 plus frames per second, even when workload changes. Image acquisition. The first step is capturing incoming video frames from the camera sensor. We use something called as a ring buffer, which basically means the camera is always collecting frames in a loop. This is important because it prevents the system from dropping frames if the processor is busy. So even if there is a temporary spike in processing, the camera keeps capturing smoothly. Pre-processing. Once a frame is captured, the next step is pre-processing. This includes tasks like resizing the image, adjusting the colors, and normalizing the pixel values. These steps must be extremely fast, ideally under 10 milliseconds per frame. To achieve this, we use SIMD acceleration, which allows multiple pixels to be processed at once. In simple terms, pre-processing is about getting the image into the exact shape and format that AI model expects. Neural network execution. Next comes the core steps, running AI model on the frame. On mid-range hardwares, this takes about 30 to 45 milliseconds depending on the complexity of the model. This is where the camera detects objects, identify patterns, recognize the faces. This model has already been optimized for our previous pipeline, so it can run quickly even with limited hardware. Post-processing, making the output useful. After the model gives its predictions, we perform post-processing. This includes tasks like filtering noise, applying thresholds, drawing bounding boxes, or converting raw model outputs into actionable results. For example, instead of just giving numbers, the system says person detected, confidence 95%, or no anomaly found. This steps prepares the results for app, user interfaces, and automated decision-making systems. These 4 steps, capturing, pre-processing, AI inference, and post-processing, work together continuously to maintain real-time performance. Even when the camera faces variable workloads, the architecture ensures smooth processing without delays at frame drops. This is what allows smart cameras to react instantly and operate reliably without depending on the cloud. Energy efficiency optimization. Now let's talk about energy efficiency, which is one of the most important parts of deploying AI and battery-powered IoT cameras. Edge devices cannot afford to waste power, and this slide explains how we reduce energy usage by 60 to 70% compared to the cloud-based systems. Computational optimization. The first area is computation. Running AI models normally requires a lot of CPU cycles, especially when using 32-bit floating point operations. But on edge devices, this would drain the battery very quickly. So we use techniques like quantization and operator fusion. Quantization reduces heavy 32-bit operations to efficient 8-bit operations. Operator fusion combines multiple operations into a single step. Together, these reduce CPU usage approximately 60 to 70%, and when hardware accelerators like NPUs or TPUs are available, they offer 4 to 10 times better energy efficiency per interference. Memory optimization. The second area is memory. Most people think computation uses most power, but in reality, accessing DRAM actually consumes 100 to 200 times more energy than performing a math calculation. To solve this, we compress models, use efficient data structures, and carefully manage memory buffers so that data is reused instead of repeatedly loaded from DRAM. This greatly cuts down unnecessary memory access and saves significant energy. The final area is controlling the camera's other components like sensors, radios, and supporting hardware. We don't keep everything running at full power all the time. Instead, we use smart scheduling. The camera sensor reduces power during low activity. Wireless radio transmits data only when needed. AI interference happens more frequently when motion is detected and less often when the scene is ideal. By adapting to real-world conditions, the system saves a large amount of energy while still delivering accurate results. So overall, Through this computation optimization, memory efficiency, and smart peripheral control, we achieve massive reduction in energy usage. This is what makes Edge AI practical for long running IoT cameras that need operate reliably for days or even months without frequent charging. Performance evaluation. Now let's go over the performance evaluation results. This slide shows how well we optimized neural network runs across different hardware platforms, and it highlights why Edge AI is strong replacement for cloud-based processing. Memory footprint. This is the first metric. Our optimized model is extremely lightweight, only around 600 KB in size. Even when we include runtime buffers and intermediate tensors, the total memory used is only 4 to 8 MB. To put into perspective, a typical edge device today comes with 1 GB of RAM. So our solution uses a small fraction of that, around 3%. The small footprint is what allows low-cost boards like Raspberry Pi or entry-level IoT chips to run advanced AI without any memory pressure. Energy consumption. Next, we look at how much energy each frame requires during pre-processing. Running AI models continuously can drain batteries quickly, but our optimizations significantly reduce power use. On a regular ARM CPU, each frame uses 0.5 to 0.8 joules. But when we use dedicated AI accelerators like NPUs and TPUs, that number drops to just 0.1 to 0.2 joules per frame, almost 5 times improvement. And if you compare this a cloud-based setup, when devices must stream video continuously, the energy difference is more dramatic. Cloud streaming can consume up to 3 joules per frame, meaning Edge AI is more efficient for long-running deployments. Bandwidth savings. Finally, let's talk about bandwidth. When cameras process videos on device itself, the only send important events or small summaries to the cloud, not full video streams. Cloud streaming usually needs around 1.2 to 1.8 Mbps per camera. But with Edge AI, we reduce this number to 50 to 200 kbps. This is an 85 to 95 reduction in bandwidth usage. This makes deployments practical even in rural areas, construction sites, or places with limited connectivity. It also lowers monthly data costs and improves reliability. So overall, the performance evaluation clearly shows the benefits of our Edge AI. These results confirm that real-time AI on edge devices is not only possible, it is efficient, scalable, and ready for real-world deployment. Let's look at some application case studies. These case studies show how technology performs outside the lab in real-world environments with real challenges. Smart doorbell security. Our first example is smart doorbell camera built on Raspberry Pi 3. Even though this is an entry-level platform, the optimized AI model performs extremely well. By processing video directly on the device, we achieved 72% reduction in bandwidth usage, 4.25 times improvement in battery life, instant on-device detection, better privacy since raw video isn't not uploaded. In case study 2, industrial defect detection. This second case study is from an industrial automation environment. Factories often use dozens of cameras to check defects on fast-moving production lines. In this prototype, 50 plus smart cameras were deployed. With Edge AI, each device could detect anomalies in under 100 milliseconds, which allows system to catch defects immediately. We also reduce the data being transmitted by over 90%, which is extremely important in factories where network stability cannot be guaranteed. This real-time response is something cloud processing simply cannot deliver. The third example is smart home security setup with multiple cameras. In many homes, internet bandwidth is limited, and people also care deeply about video privacy. Edge AI solves both the challenges. The systems analyze the video locally and sends only essential alerts to the cloud. This reduces streaming cost, protects user privacy, and ensures the system works even when internet is unstable. These case studies clearly demonstrate Edge AI is practical, scalable, and ready for different industries. Future directions. Now let's move on to what the future looks like for Edge AI systems. The technology is evolving rapidly, and the next steps will make smarter devices even faster, more private, and more intelligent. Federated learning. In the future, devices will be able to learn from new data without sending raw images to the cloud. Instead, each device trains locally and sends only model updates, not videos. This keeps data private while improving the overall accuracy. This approach is perfect for home cameras, healthcare devices, and any systems where privacy is important. Collaborative edge intelligence. Another exciting direction is device to device collaboration. Imagine multiple cameras in a home or a factory sharing the workloads. If one device is busy or has low battery, another device can take over the processing. This creates a distributed intelligence layer where devices support each other. It makes the whole system more reliable and efficient. Next generation hardware. We expect more powerful NPUs, TPUs, and specialized AI chips with much higher performance per watt. Devices will run larger AI models without consuming more power. This enables analytics like multi-object tracking, behavior prediction, and even on-device video summarization. Standardized application framework. Finally, we expect platforms that allow developers to build once and deploy anywhere. This means AI applications will run across all types of hardware, from doorbell cameras to industrial robots, without major rework. These advancements will help speed up adoption and reduce development cost. Conclusion. To conclude, Edge AI is not just an enhancement. It represents a complete shift in how smart camera systems operate. We are moving from cloud-centered intelligence to a world where intelligence lives directly on the device. Throughout the presentation, we have seen this approach gives us major improvements, like under 50 milliseconds latency for real-time processing, works on devices with little as 512 MB RAM, 80% or more reduction in bandwidth usage, 4 to 5 times improvement in battery life, high reliability, even low connectivity environments. These results show the Edge AI is practical, efficient, and highly scalable. As a final statement, the future is smart camera is edge first. With optimized AI models, efficient hardware, and intelligent software architecture, we can unlock fast, private, and reliable AI. Thank you. I'm happy to take any technical questions.